In the previous class, we learnt how to generate code word for any message vector for a n comma k linear code using a generator matrix. So, the generator matrix is of the size k by n, and the rows of the generator matrix are k independent vectors which span the k dimensional subspace of a higher n dimensional vector space of n tuples. We also studied a subclass of linear block code known as systematic linear code. In systematic linear code, the last k elements of a code word exactly match with the corresponding k elements of the message vector. The generator matrix of such a linear code is expressed as shown here on the slide. So, this is the parity array and this is the identity matrix of size k by k, and the matrix G is of this form. Now, based on our discussions, we can easily observe that each of these rows of this generator matrix G correspond to the code words of the unit message vectors, where a unit message vector is defined as a message vector with only one non-zero element. So, this row is a code word for this message vector, this row is a code word for this message vector, and similarly the last row is a code word for this unit message vector. Now, any message signal which is k tuple can be represented in terms of this unit message vectors. So, the code word for this message vector is the linear combinations of this code words for the unit message vectors. Now, in the literature, the generator matrix is also written in this form, where the parity array follows the identity matrix of size k by k. Now, in this case, the first k elements of a code word will be exactly matched with the k elements of the corresponding message vector. Otherwise, the code properties remain unaffected. So, as far as our discussion is concerned, we will consider our generator matrix to be of this form. Now, for any generator matrix, there exists what is known as Parity-Check Matrix H, and the property of that matrix H follows. What it says, that there exists an n minus k by n matrix Parity-Check Matrix H such that the rows of G are orthogonal to the rows of the Parity-Check Matrix H. That is, G H transpose is equal to a 0 matrix, where this 0 matrix is of the size k by n minus k, and it contains all 0 elements. So, the Parity-Check matrix for the matrix G is as shown here on the slide. So, you have an identity matrix of size n minus k by n minus k followed by the transpose of the parity array. And so, H transpose would be the transpose of this, transpose of this. So, we get the H transpose matrix this, and we know what is the parity array. So, if we substitute the values for that, H transpose matrix is as shown here. Now, once we write H transpose matrix and G matrix, it is easy to see that GH transpose is equal to a 0 matrix. So, this slide clearly demonstrates that GH transpose, this is G matrix and this is H transpose is equal to 0. So, if we take the first row and multiply with the first column out here, correct, you will get P11 and rest of the terms here will go to 0, and then you will pick up again P11. So, what will be picked up is P11 plus P11. So, that would be equal to 0, and then if you multiply this by this, again you will pick up P12 and here you will pick up P12. So, P12 plus P12, again this would be equal to 0, right, using the modular 2 arithmetic. So, any row multiplied with any column out here will give you 0, and similarly you can take any other row in the G matrix and multiply with the column out here, it will turn out to be 0. So, GH transpose is a 0 matrix. Now, we know that our code vector U is as shown here. We have first n minus k parity bits followed by k bits representing the message. This is the systematic form of the code word, and this parity bits are obtained by this relationship which we have seen last time. It is a linear combinations of the elements from the parity array, and with this definition of our code word, it is now easy to see what happens when I take U code word and multiply with H transpose. So, this is my code word U and this is my H transpose. So, if we take this and multiply by the first column out here, we will get P11 plus you will get the linear combinations of this weighted by M1 to Mk, and similarly if we take this and multiply with the second column out here, we will get P2 plus the weighted combinations of these elements by M1, M2 up to Mk. So, on multiplying U by H transpose, it is easy to see that we get the following result. The first element in this would be P1 plus P1, the second would be P2 plus P2, and the last one would be Pn minus k plus Pn minus k. Now, this will be all 0. So, we get a 0 row vector of size 1 by n minus k. So, what it says that the code word when multiplied by H transpose would give you 0, correct. Now, this is a very powerful result which can be used to find out if the received vector is really a code word or non-code word, and this can be done as follows. This is known as syndrome testing. So, we have a received vector which is the transmitted vector u plus, let us assume there is some error vector. So, this error vector is also n tuple. So, the receive vector is the sum of the two. Now, if we compute R multiplied by H transpose, if R is a valid member of code word set, then this syndrome would be equal to 0, otherwise it would be non-zero. This is very clearly seen if we write the expansion as follows. So, S is equal to R multiplied by H transpose, R is U plus E multiplied by H transpose. So, I open out the bracket, I get UH transpose plus EH transpose. Now, we know that UH transpose is equal to 0. So, the result would be E multiplied by H transpose. So, what this result shows, that the syndrome which we get on multiplying the receive vector by H transpose is same as the syndrome which we will get if we take the error pattern which has corrupted the transmitted code word and multiply it with the H transpose, you will get the same result. So, if R contains detectable errors, then the syndrome will be non-zero, and if R contains correctable errors, then also the syndrome will be non-zero, but in this case we can identify the particular error pattern. This will become very clear as we proceed ahead. But the important thing is that on receiving the vector on multiplication with H transpose, the 0 value tells us that the received vector is a code word, and if it is non-zero, it says the received vector is non-code word. What to do later on we will see as we proceed ahead. But there are two required properties of this parity-check matrix, and these are as follows. The first is no column of H can be all zeros. So, what this implies, that no row of H transpose can be all zeros. Now, this is easy to see why this condition should be satisfied, because if it were true, then error in the corresponding code word position would not affect the syndrome, and the error would go undetectable. Look here, if any of the column of H is 0, that means the row of H is 0. If there is error in that position, this row being 0, the syndrome will not get affected, because if the error is there in this position, because of all zeros, it will go to 0. There will be no contribution from that error, and that is why this will go undetectable. Okay? And the second is that all columns of H must be unique. So, what this implies, that all rows of H transpose should be unique, because if that does not happen, then the error in two positions will be indistinguishable. For example, if I have error corresponding to this position, so this will be at this point. If I have an error at this point corresponding to this row, and I have error say at this point corresponding to the second row, if both are identical, then I am not sure whether the error has occurred here or the error has occurred here, correct. So, that is why we say that the rows of H transpose should be all distinct, implying that the columns of H should be all unique or distinct. So, if that condition is violated, then errors in these two corresponding code word positions would be indistinguishable. So, let us take one simple example. Suppose I have a transmitted code word to be of this form, and then let us assume that there is an error in the first bit of the transmitted code word. So, we get the receive vector to be as shown here. So, there is an error in the first bit. Now, if we calculate the syndrome for this by multiplying R by H transpose, and H transpose, we choose the same generator matrix which we had chosen in the previous class as an example, and for that generator matrix we can write the H transpose, and then we multiply this, we get the answer to be, after multiplication, equal to this, which is equivalent to 100, 100, correct. And if we take, we know that there is error only in the first bit, so the error pattern is 1 0 0 0 0 0, and if we take that error pattern and multiply with H transpose, we get 1 0 0 0. So what this says, what we had said earlier, that syndrome obtained by taking the multiplication of the received vector with H transpose is the same as the syndrome which we will get on multiplying the error pattern with the H transpose. Okay. Fine. Now, we would like to understand the error detection and correction properties of a linear code. Now, in order to do that, we need to understand some preliminaries, and let us do that first. So, the first thing is the concept of Hamming distance. The Hamming distance is defined as the number of components at which the two code words UI and UJ, UI is corresponding to the message vector Mi and UJ is corresponding to the message vector Mj. So, the number of components at which the two code words UI and UJ differ, and this is denoted by this notation, is the Hamming distance between the two code words. Then there is a concept of Hamming weight, which is defined as the number of non-zero components of the code word UI, and this is denoted by WUI. There is a concept of minimum distance of a code. A code consists of a set of code words corresponding to the set of message vectors. So, the minimum distance of a code is the minimum Hamming distance between any two different code words in the code. So, D minimum is equal to minimum, you have to calculate between all UIs and UJ, assuming that UI and UJ are not the same. So, for whichever two code word where we get this distance to be minimum, that distance between the two code word is defined as the D minimum, and that forms the minimum distance of a code. Now, the minimum weight of a code is the minimum of the weights of the code words which are there in the code except the all zero code word. So, W minimum is minimum of this weight where UI is not equal to 0 vector, all 0 vector, because all the linear codes will have all 0 vector has one of your code word. This we have seen in the earlier class. This is a requirement for the code to be a linear. Now, there is a theorem which says that in any linear code, D minimum is equal to W minimum. So, remember, D minimum is the minimum distance of a code and W minimum is the minimum weight of a code word in the code. So, the proof follows as follows. If say U is a code word, then the weight of this code word is the same as this should be distance. So, this should be distance between u and all 0 code word. So, this is equal to distance, correct. So, now if ui and uj are code words, then if we take the sum of ui and uj, then because this belongs to a linear code, this sum is going to be some code word in that code. So, what it implies that the distance between ui and uj is equal to weight of this code u, correct. So, from this it means that in a linear code corresponding to any weight of a code, there exists a Hamming distance between the two code words, and corresponding to any Hamming distance there exists a weight of a code word. So, in particular it follows that d minimum is equal to w minimum. So, we have proved that in any linear code d minimum is equal to the minimum weight of a code, which is w minimum. Now, let us take example. So, if I have say two code words u and v, which are 6 tuples each, then the distance between the two code words is given by the number of components at which the two code words u and v differ. So, 1, 2, 3, 4, 5, 6. So, the distance here is 6, and the weight of this code u is equal to the number of non-zero components, which is 1, 2, 3, and similarly the weight of this code v is 1, 2, 3, we get 3. Now, having studied this concept of Hamming distance, Hamming weight, then the next question is, how are this d minimum, w minimum helpful in deciding the error correction or error detection capability of a linear code? We will try to find the answer to this question next time. Thank you.